This So good afternoon, guys. Those who have joined online, can you hear me, please? Are you getting my audio? Some of you can respond.
Yes, sir.
Yeah, thank you. So my name is G. Rajshekhar, and I'll be dealing with this course called Digital Electronics and Logic Design for you in this semester. So basically, I teach subjects which are related to EC, electronics and communications engineering background. Okay. So in IT also we have some important subjects related to ECE branch. Okay, like you had in the previous semester basic electronics. This semester you have DELD. In the later semester, not in the fourth semester. Fourth semester you have computer organization. Later on in the fifth semester you will have microprocessors and interfacing. Then in the next semester you have embedded systems and IoT. So this sequence of courses are somehow related to ECE branch. Okay, but being IT students, you also study these courses as they are helpful to you. Okay, you will get knowledge about the architecture details, how the processor is designed, what are the operations which are performed by the processors which are used. Okay, so all these things they are covered in the electronics stream of this program. So the second course in this list is Digital Electronics and Logic Design. So already you have studied in one course in the previous semester, Basic Electronics. I hope you got some knowledge. I mean, the bad thing is you guys did not get any opportunity to see how a electronic component will look like. Okay, so without knowing, without physically seeing the components, actually you have gone out of the second semester, came into the third semester where you are studying all core subjects. So even then, at least maybe you had some idea of how the electronic devices are used in order to build smaller circuits. Okay, like rectifiers, clipping circuits, clamping circuits. Okay, so I mean, if you had a physical lab, you would have experienced it in a much better way. But due to this COVID, we are not able to conduct that physical lab. Okay, but maybe in the coming days, at least you will get to know some of the hardware labs like microprocessor and interfacing, and the other one is embedded systems and IoT. Okay, so that is the stream of courses in the electronics related subjects which you are going to study in your 4 years of BE course there. So in this semester, we are discussing digital electronics and logic design. Okay, so there are 3 faculty who are handling this course for the second year students, particularly third semester students. Each of them is going to 3 sections there. Okay. So online guys, are you getting my audio clearly? Online guys?
Yes, sir, clear.
I see only 37 have joined. What about others, man? Are they going to join or not? Yes, somebody please respond. Are they going to join? What was the strength in the morning classes? Anybody here? Online, what was the strength there in the morning? 50? 57. Oh, I see only 37 have joined. 37, here there are 10 guys. 47. Total strength is 60. Huh? 60. So anyway, please ask your friends to join on time. Why? Because I'll not be allowing anybody into the class after the first 5 minutes. Okay, from the next class onwards. Only today there is an excuse I am giving you. So those who are online, please inform your friends about this condition. So if you join 5 minutes late, you will be just waiting in the lobby there. I will not allow you into the class. So please take care of those things and join on time so that you understand what is being discussed. Okay. Online guys, can you see my slide PDF which is shared to you?
Yes.
Yeah. So what do you see? What do you see?
Courses, sir.
So this is the list of courses which you are going to study in this semester. This is not the list from your your batch, but I am using from the previous batch to display it to you. I mean, your syllabus is not yet put in the website there. So very soon they will keep your syllabus of the entire academic year in the website very soon. So just to know what is that you have in this semester, just is the scheme of your courses in this semester. So these are the set of courses, and one of the courses is digital electronics and logic design, and the course code for you would be U20 ES 310 IT. Okay, for your batch the course code would be U20 ES 310 IT, where U stands for undergraduate, 20 stands for when is the starting year of your joining. So when did you join? That is the second two digits here. So your batch will get 20 here, U20 undergraduate 2020 joining batch. Then ES for engineering sciences, 310 is the sequence of the course here, the sequence number of the course here in this list. Okay, third semester, third semester, one for theory, something like that is there. I don't remember exactly. So this is the course which we are going to discuss in the semester, digital electronics and logic design. Okay. Now let us have a look at the syllabus of the course. Online guys, can you see the syllabus now? Online guys?
Yes, sir.
Yeah. So this is the syllabus of your course here, digital electronics and logic design, which I'm going to deal in this semester for you guys there. So as you see here, this course is basically, are you getting my audio clearly there, online guys? Audio is clear?
Yes, sir, it is clear.
Yes, sir.
Fine. Okay, so as you see here, this is the syllabus of digital electronics and logic design course, which you are going to study in this semester. So basically, what this course talks about is, sir, I'm in class, sir. Yeah. So this is the subject of digital electronics and logic design. So basically, here in this subject, what we are going to study is we try to understand how we can design digital circuits. So in the last semester, you had this basic electronics course where you were trying to design circuits which were analog circuits. Analog circuits means these were circuits which were built or designed or constructed using the discrete electronic components. Okay, like you had your diode. Okay, using the diodes, you can design various circuits: half-wave rectifier, full-wave rectifier, okay, bridge rectifier. Okay, you had clipping circuits, you had clapping circuits, where we were using electronic components like diodes, resistors, capacitors in the design of circuits. Okay, so those kind of circuits are called as analog circuits. Okay, so these analog circuits are constructed using electronic components. Okay, examples of electronic components can be your diode. Transistor is one more example. Transistor is a three-terminal device which you have seen, bipolar junction transistor. Then we have other electronic components like FET was there. Okay, field effect transistor, which is once again a three-terminal device. Okay, then you had operational amplifier IC. So this was a component which was available for us in the form of an integrated circuit. Okay, we can use this IC to design various application circuits. You have seen in the last semester how we can design adder functionality, how we can design multiplier. Okay, or we can design an integrated circuit where whatever signal is coming to that will be integrated. Okay, a differentiator. Okay, some are difference amplifier. All these things we have studied. Okay, so that was the discussion which had happened in the previous semester, which talking about how we can design circuits which are called as analog circuits. Analog means they are designed using discrete electronic components. Okay, like as I mentioned now. Okay, now here in this course, what we are going to understand is we are going to understand circuits which are referred to as digital electronic circuits. So examples of digital electronic circuits is you have this system, right? This is you have your desktop system on the laptop, right? That is an example of a digital system. That is an example of a digital system. So within that, there are so many small circuits inside that. Okay. So one principal circuit which you can see is the processor. Processor is available as a chip. Okay. All of you know what is a processor, right? All of you are using laptops or desktops at your homes, right? So every processor, every system, every laptop or a desktop will have a processor in it. Okay, all of you know what is a processor, right? So nowadays you are using the PCs which are having i3, i5, i7 processors, right? So these are examples of digital circuits. Okay, so the IC which you see, the integrated circuit of the processor chip which is placed inside the system box there, that is an example for a digital system. Okay. There, the IC, within the IC, what we have is we have so many logical gates which are interconnected together. And all of you know, I think you know what are logical gates, right? You know what are logical gates? Somebody online, offline, anybody?
Yes, sir.
So what are logical gates? So we can perform various operations with data. We can perform various operations with data. It can be arithmetic operations or it can be logical operations. Okay. So these logic gates are some basic electric circuit, basic digital circuits which help us to do logical operations. Okay. These are the basic digital circuits which help us to do logical operations. So I can have a gate which can do logical AND operation. Okay. So two inputs you give, it will just AND the values of these two inputs and give us the output there. Okay, logical AND operation it will do on the input supplied to it. Okay, so that's an example of a basic logical gate. Okay, your simplest gate is AND gate. Similarly, I can do, say for example, I have a signal called signal which is 1, which is applied to a NOT gate. And all of you know what is a NOT gate? You just complement the value. So 1 becomes 0, 0 becomes 1. Okay. So all these basic logical operations which you can do, they're actually constructed, they're actually designed in the form of logical gates. And when you connect these logical gates, many logical gates to form a bigger circuit, that circuit will form what is a digital system for us. Okay, what is an example for a digital system for us? So a processor, maybe internally it is constructed using so many logical gates. Okay, so this forms a bigger system for us. Okay, so that's an example for a digital system for us. That's a digital electronic circuit for us. A processor IC is an example for a digital electronic circuit for us. Okay, so when you're talking about processor, what kind of data this processor deals with? What kind of data the processor works with? Anybody? So you are using your laptop every day, right? So the processor or the machine understand what kind of data. Does it understand? So I say 1, 2, 3, 4. Does it the processor does it understand 1, 2, 3, 4 or any other type of data it will understand? Huh? It will understand zeros and ones only. So the circuit at the lowest level will not understand anything which you are writing in the high level language or high level program, but at the lowest level it will understand only ones and zeros. So my digital circuit operates with what kind of signals? The digital circuit operates with binary signals. Okay, binary signals can take either a value 1 or a value 0. And this binary signal you normally call it as a bit. Okay, a bit can be a bit is a binary digit. Okay, so this can take a value either 1 or 0. So how do you represent this 1 and 0 at the lowest level? So at the lowest level we represent 1 with a voltage level, voltage pulse, something like this. So I can have whenever I want to represent a logical value 1, so what I can say is whenever, say for example, I want to represent logic value 1, logic 1. So my signals at the lowest level will be something like this. Logic 0, it can be logic 0 or logic 1. So my signals at the lowest level will be a signal like this, a pulse kind of waveform, where this can take 0 volts or this can take 5 volts. So whenever the signal is taking a value of 5 volts, as illustrated at this in this period, so this value of the signal is considered as logical value 1. Okay, and wherever the signal is going at a 0 volts value, this is considered as logic 0. So the logic, the binary values, whatever the machine understands, okay, the binary values, whatever the machine understands, they are actually voltage signals for us. So this is an example for a voltage signal. So you are representing the logical values using voltage signal. In this case, we are representing 5 volts for a logical value 1. You are representing 5 volts for logic value 1, and you are using 0 volts for logic value 0. Okay, something like this. Okay, so at the lowest level, the machine will understand only these kind of pulses. The machine will understand only these kind of pulses. So based on these kind of pulses which are coming to the circuit, it will do the corresponding operation and it will give you the results for that operation. Okay, it can be either your arithmetic addition, or it can be a logical AND operation, a logical OR operation, or whatever, any kind of operation that happens on these kind of signals only. So whatever signals you see, these kind of signals will be appearing at the lowest level in the system. So you are supplying some power to the PC, right? So that means you are applying a voltage signal to the circuit here. That voltage signal internally goes through different logical gates and gives you the desired output. Okay. So that is what happens internally in the system there. So in this circuit, in this course, what we are going to understand is we are going to try to understand the various types of digital circuits. Okay. So we are going to understand in this course the various types of digital circuits. So digital electronics and logic circuit, we are going to understand the different types of digital circuits which we can design. Okay. So these digital circuits are once again divided into two categories. These digital circuits are once again divided into two categories. So what are the two categories? The first one is referred to as combinational circuits. The first type of digital circuits can be your combinational circuits. So this is an interesting subject which you are studying in this semester. I mean, don't keep basic electronics in your mind here. So this is a relatively easy subject when compared to basic electronics. So you should have that motivation to follow the discussion every day, so that it becomes easy for you. Okay. So basically, we are dealing with digital circuits in this course here. So digital circuits are categorized into two types there. First type is what is referred to as combinational circuits, and the second one is what is referred to as sequential circuits. Second one is referred to as sequential circuits. So these are the two important types of circuits which we are going to study in this course. So in the entire course of your digital electronics and logic design, we'll try to understand how we can design these combination circuits. We'll also try to understand how we can design sequential circuits. Okay. Now, once again, if you look at further classification, these sequential circuits, they are once again divided into two types. We can have what are referred to as synchronous sequential circuits. We can once again have synchronous sequential circuits, and we can have asynchronous sequential circuits. So whatever I'm writing here, the entire course, in the entire duration of the course, we are going to understand the design of these different types of circuits. Okay. Now, what are combination circuits? So what are combination circuits? So combination circuits, the main point you need to understand here is these circuits are basically constructed using logical gates. These are basically constructed using logic gates. So combination circuits, the entire circuit is actually constructed using what are referred to as logical gates. So we are going to understand what are logical gates, and all of you know the basic logical gates. So the basic logical gates are your AND gate, OR gate, XOR gate, NOR gate. Okay. So these circuits, combination circuits, are actually constructed using these basic logical gates. Okay. Now coming to the sequence circuits. So these circuits are also constructed using logical gates. So in addition to logical gates, they also involve what are referred to as memory elements. What are referred to as memory elements. So that is the only difference between the design of a combination circuits and sequence circuits. So the combination circuit, there are actually constructed, the entire circuit is made up of logical gates only. But when you talk about sequential circuits, there actually the circuit is made up of a combination of logical gates. Along with that, there are some additional circuit elements which are referred to as memory elements. Okay, so these circuits are constructed using a combination of logical gates as well as memory elements. Okay, so whenever I say memory elements, so I'll be able to store information here. So in this type of circuits, I'll be able to store information. So whenever you're talking about sequence circuit, you can store some information. Store information. As they have memory elements there, they can store some data for us. Okay, they can store some data for us. Okay, now let us see some examples of combination circuits and sequential circuits. Okay, so I'll just list out some of the examples of combination circuits. Some examples can be your, I have a circuit internally which performs addition operation, adder circuit. So you write in a high level language program, say for example, you use C language. You use C language and write a program saying that C equals to A plus B. So what I'm doing operation here in this syntax here. So what I'm going to do, I'm going to add, say for example, I'm operating with 8-bit data. If I'm operating with 8-bit data, so what I'm going to do here, I'm going to add two 8-bit numbers. Do you agree or not? Yes. So when you say int A, int B, and say int C, then add say int C equals to A plus B. So what will happen there? The two values A and B will be getting added, and the result will be stored in C. So what happens is, so every time an operation like this is written in the higher level, so at the lowest level, what happens is this operation will be converted to the equivalent circuit at the lowest level. Equivalent circuit at the lowest level. This operation which is done on the higher level will be converted to an equivalent circuit at the lowest level, that at the machine level. So here, in order to perform this operation, what circuits you think you require? The first thing you require is some storage space, right? You require some storage space for storing the values of the operands. Do you agree or not? Do you agree or not? So here at the highest level, what we are considering A as a variable, B as a variable here. So I have two variables at the highest level. So when you talk at the lowest level, at the machine level, so the variables at the higher level will be converted into what are referred to as registers at the lowest level. We have something called registers at the lowest level. So every variable you declare at the highest level will be having a register at the lowest level. Okay, so here the variable you have declared as int. So let us assume that int takes 8 bits. Int take 8 bits. Let us assume that. So in that case, what should be the size of register here? Every register size should be 8-bit register, right? I have an 8-bit data coming there in variable A. I have an 8-bit data coming there in variable B there. So at the lowest level, I need to store this data. So where I store, I should have some storage space. That storage space we are calling it as register. So my variable is of type int. So what should be the size of the register there? Size of the register should be an 8-bit register. So whatever variable you are declaring at the higher level, so that is creating some storage space internally in the system or internally in the processor circuit there, and that storage space is what is referred to as registers at the lowest level. So what are registers? Registers are nothing but this is some kind of circuit which should help us in order to store 8 bits. Okay, register is nothing but a circuit which helps us to store 8 bits of data. Okay, so I'll just write it here. Circuit, what is a register? Circuit that helps in storing. It can be more than 8-bit as well, but here since we are taking the example of an int which is taking 8-bit size, so that circuit that helps us in storing 8-bit data. Okay, we'll consider the simplest case. So every variable you declare at the highest level is once again at the lowest level, it converts to a register where each register is capable of storing 8-bit data. Do you agree? Now, So that is one aspect of that operation which we are doing. So I should have some storage space for storing my operands A and B, which are stored in registers now at the lowest level. Now, what is the other thing you require in order to implement that, in order to execute that instruction at the higher level? So what, you are doing some certain operation, right? What is that operation you are doing? You are doing certain operation, right? What is that operation you are doing? Add operation, right? So I should have a circuit which performs the add operation. So what circuit can perform an add operation? A simple adder circuit. So I should have an adder at the lowest level, which will take the two variables there, the two registers there, and put the data coming from the two registers and just add the binary pattern there. And after doing the addition, what I'm doing here, based on the statement which I have written in this higher level, yes, I'm storing in C variable. So whenever I store in C, a new variable is created, right? A new variable is created. So there should be some more storage space for storing the result. Register for result. Register to store the result. Result, some register where I can store my result of the operation. So this is how a high level statement like this is actually interpreted by the digital circuit sitting there in this box. Okay. So every time you declare a variable, there is a register created for you. There is a register available for you where you can store the data. Every time you do an operation there, there is a circuit coming picture which takes the data and performs that operation. And as soon as you get a result, you store it somewhere at the higher level. Similarly, at the lowest level, there should be a register where you store that. So online guys, are you there?
Yes, sir.
So there was a small problem here. So are you able to see the open board there? Whiteboard? Yes. So
Yes, sir.
okay, so in order to perform this simple operation at the higher level, we require so much of circuitry here at the lowest level. We require some storage space where you can store the binary data. We require some circuit which can help us doing the operation there. And once again, after getting the result, I should store the result once again somewhere in the lowest level. Okay, so these are the things which are required at the lowest level. So what we are going to understand here is we are going to understand how you design these things, how you are going to design these things at the lowest level. That is what we are going to understand in this course. Okay. So examples of, as I said here, in order to perform this operation, I require an adder. So adder is an example of a combination circuit. So it is, you can construct an adder using logical gates. So how do you do that? We'll try to understand in the course of the discussion. Okay. So similarly, I can have one more. You can have other subtractor of subtraction also is possible, right? You can have a subtractor circuit as well. Okay. Similarly, you can have a multiplier circuit. Okay, for multiplication of two numbers. Okay, multiplication, you require a multiplier. Okay, then in addition to this, we can also have other circuits as well. Normally, how do you? What is the pattern? The machine understands. The machine understands only binary data, right? So, do you understand how do you? So this keyboard, you are pressing some keys on the keyboard. So how this whatever you are pressing is going into the machine. So what is the code used there? What is the code used there? So whenever I press a key on the keyboard here, what is happening there internally? Some code is generated. Every time I press a key here, if you know from your programming, so every time I press a key here, a binary code is generated for me. So anybody remembers what is this binary code? EB extended. You remember? It's ASCII code. What are the other codes you have? You know ASCII. What is the size of the ASCII code? How many bits it takes? Huh? ASCII code, how many bits it will have? So every time you press a key here, an ASCII code is generated. So what is basically ASCII code? ASCII code is nothing but binary data, right? A set of bits together. This is a code for me. So here, so the machine will understand only binary code. It will not understand your ASCII, your EBC, some code is there, EBC, DIC, all codes are there. So the machine will not understand all these things. It will just understand only binary code. So, but for the user who is operating with that system there, you should know different codes using which you can represent the binary data. Okay, so you have circuits which are called as code converters. How can you convert data from one code system to other? Okay. Online guys, are you there with me?
Yes, sir.
Okay. So another example for a combination circuit can be a code converter. How you can convert from one binary code to the other binary code. Okay, we have different types of binary codes. Okay, how you can convert from one binary code to another binary code. So we have circuits which are called as code converters, which will help us in order to. Then I can have another example for a circuit, combination circuit can be, say for example, I write a if condition something like this. If A greater than B. Can I write a high-level syntax like this? If A greater than B. So what is that you are doing here? What is that you are doing in this operation? Huh? What is that you are doing in this operation? I am syntactically, I may not be correct, but I'm just asking you, can I do a condition like this? Can I put a condition like this on the higher level language, right? So what is that you are trying to do here? What is that you are trying to do here?
Condition checking.
You are checking condition, or you are checking whether the magnitude of A is greater than the magnitude of B. Yes. Am I checking the magnitude of the variables there? Yes or no? The value of the variable A, whether it is greater than the value of the variable B. Do you agree or not? Yes or no? Online guess.
Yes.
Yes.
So this is something like a magnitude comparison, which I am doing there. So I can have one more combination circuit which help us to do magnitude comparison. I call that circuit as magnitude comparator. I can have a circuit which compares the magnitude of two numbers which is coming to it. I can have a circuit which compares the magnitude of two numbers which is coming to it as input. Okay, so these are some of the examples of combination circuits. These are some examples of combination circuits. Do you agree? Yes? Online guys, do you agree? Online guys, do you agree?
Yes, sir.
So these are some of the examples of combination circuits. So all these circuits we are going to understand in our discussion. How can you design an adder circuit? How you can design a subtractor circuit at the lowest level? How you can design a multiplier, a code converter circuit, a magnitude comparator circuit? So all these things we are going to understand in this subject. So how can you construct? So all these circuits we will construct using only logical gates. So all these circuits are constructed using logical gates only. All the circuits you can construct using simply logical gates. Using basic logical gates, you can construct all the circuits. So how do you actually do that? That is what we are going to understand in this course. Okay, that is what we are going to understand in this course. Okay, so this is first part of the circuit. These are the first category of circuits which are referred to as combination circuits. Am I clear till this point? Online guys, offline guys? Yes? Yes or no?
Yes.
Online guys? Okay.
Yes, sir.
Now, what is the second category of circuits just now we have understood? What is the second category of circuits which we have just now understood? Huh? Second category of circuits is what is referred to as sequential circuits. What are referred to as sequential circuits. And just now we have seen we require some storage space. So we require some storage space. Storage space means I should be able to store data. I should be able to store my data. And what is data for us? Data is binary data for us, right? So I should have a circuit. I should have a circuit which help us, a circuit which can store binary data for us. I should have a circuit which can store binary data, and that circuit we just now referred it as a register at the lowest level. We call it as a register. So what is register? We have mentioned the size of the register as well. We said I want an 8-bit register at the lowest level. Whenever I declare an int variable at the highest level, the storage space is a register which is 8-bit in size. Okay. So what is this register? Register is nothing but something like this. I should have some storage space like this, wherein 3, 4, 5, 6, 7, and 8. So this is a register for us. Okay. So here, every individual block which you see here is able to store 1 bit of data. Every individual block here is able to store 1 bit of data. So the circuit which helps us at the lowest level in order to store this 1 bit of data is what is referred to as flip-flop or the memory element. So what is referred to as flip-flop, F-L-I-P, F-L-O-P, flip-flop, and this is the memory element at the lowest level. This is the memory element at the lowest level. So my register is nothing but it's a collection of flip-flops together. What is my register now? So I said every square here is storing 1 bit of space, and that storage space is storing 1 bit of information. I am referring it as flip-flop there. So what is my register now? Register is nothing but a set of flip-flops connected together. A register is nothing but a set of flip-flops connected together. So in order to have an 8-bit register, what I do, I connect 8 flip-flops together like this so that I will be able to store 8-bit of data for us. I'm able to store 8-bit of data, right? So at the lowest level, this storage element, what you see is called as flip-flop, and this flip-flop is the memory element there. And whenever I say memory element, it is able to store some information for you. Your memory means holding something in it. Okay, so the circuit is able to hold some information in it. That's why we are referring to as memory element. It is able to store some data there. So the flip-flop can hold 1 bit of data. So you require 8 flip-flops there to form an 8-bit register. Yes. So circuits which help us in order to store binary data, they are example of sequential circuits. Okay, these kind of circuits, all the storage elements are examples for your sequential circuits. So these circuits are actually constructed using a combination of logical gates, combination of logic gates and memory elements. So all circuits which are helping us in order to store some data, binary data, and these circuits are called sequence circuit, and they are constructed using logical gates. In addition to logical gates, we also have certain elements which are referred to as memory elements. So what are these memory elements? And memory element is nothing but a flip-flop. So how this flip-flop is actually implemented at the lowest level, we'll try to understand in the course of the discussion. But just now at the highest level, just understand that we are able to classify the digital circuits into two categories there. One category is referred to as combination circuits. Now you know the examples of combination circuits, and these combination circuits can be constructed using only logical gates. Now the other category of circuits, digital circuits, which you can design are referred to as sequential circuit. They help us in order to store some information. An example can be a flip-flop which can store one binary information, one bit of data for us. And when you connect multiple flip-flops together, that becomes a register for us, which can store an 8-bit data if you declare it as an int data. Okay, and these circuits are referred to as sequential circuits. Okay, and they are constructed using a combination of logic gates as well as memory elements. Okay, so that is what we are going to understand. Now here I said there are two types. Once again, sequential circuits, we have two types: synchronous sequential circuits and asynchronous sequential circuits. So when these circuits operate with respect to the clock signal, so the processor has a frequency. Every processor you use has a frequency there. So how do you, I mean, you go to purchase a laptop. So what do you say? I want i5 or i3 processor with some gigahertz frequency, right? Okay, do you say that or not? When you purchase a laptop, you ask for specifications, right? I want an i5 processor with so many gigahertz of frequency. Okay, you say that or not? Online guess. So the term which you are using there to specify the processor is related to what is referred to as frequency. So where is this concept of frequency coming from? So all the circuits which are lying in that processor IC, processor is a digital system for us. It is consisting of so many circuits. So there are so many small circuits which are interconnected together to form the bigger processor chip. Okay, small digital circuits which are interconnected together to form the bigger processor chip there. So I need to synchronize. I need to properly operate all the circuits together to form the bigger circuit of the processor IC there. So in order to have this proper synchronization with all the smaller circuits of the processor chip there, I require some clock signal applied to the processor there. So every processor comes with what is referred to as clock. So whenever you are talking about sequence circuits, I can have two types of circuits here. One is referred to as synchronous sequence circuits. So first one is called as synchronous sequential circuits. Synchronous. So synchronous circuits, what they do is they operate with respect to the clock signal. So every operation of a synchronous sequence circuit is synchronized with respect to the clock signal. So the other category which we have is what are referred to as asynchronous sequential circuits. So here clock does not have any role to play here. My operation is not related to the clock signal coming there. Okay, so in this way we can have two types of sequential circuits. One is referred to as synchronous sequential circuits. The other one is referred to as asynchronous sequential circuits. So synchronous circuits, they operate with respect to the clock signal. Asynchronous sequential circuits, they do not operate with respect to the clock signal. So this is the entire discussion which we are going to make in this course actually. Okay. So in the entire course of this semester, we are going to understand how you can design various combination circuits and how you can design various sequential circuits. Am I clear till this point? Online guys?
Yes.
Online guys, am I clear till this point?
Yes, sir.
So now, do you have any motivation to study this course? What is the requirement for you guys to study this course? Do you find any reason for studying this course now? Do you find any reason for studying this course? So, online guys, one of you can respond.
To write programs effectively by understanding how the low level works.
Yeah, that is correct, man. So if you understand how the machine operates at the lower level, you can write more effective programs at the higher level. Yes, agree or not? So what kind of data type I need to use? So based on processor, whether I can work with 64-bit data or whether I need to work with 8-bit data or whether I need to work with 32-bit data, that decision you can make at the higher level if you know what kind of processor you are working on. So say for example, I'm working on a 32-bit processor and I have a 64-bit data which is coming to me. Can you use this 64-bit data on the 32-bit processing machine? No, right? So you have to use two cycles for performing the operation, right? So if you know the internal architecture, so how the digital system is designed, if you know that, you'll be able to write your programs in a more effective way. Okay, so that discussion we are going to make in this subject of digital electronics and logic design. So we are going to understand how the machine, so how the processor chip is actually designed. So how various smaller digital systems you connect together to form a bigger processor chip. Okay, that is what we are going to understand in this course of digital electronics and logic design. Yes, so that is the motivation for studying this course. Now, once again, let us come back to the syllabus there. So the first unit here, it is basically talking about the basic fundamentals from mathematics which you require for doing digital circuit design. So whenever you want to design digital circuits, you require some basic mathematics there. So this mathematics is nothing but Boolean algebra you require. So we study some of the fundamentals of Boolean algebra here in the first unit, and how you can use this concept of Boolean algebra in digital electronics and logic design. That is what we are going to study in the first unit. So the required mathematical fundamentals are studied in the first unit. Okay. So these will be the topics of the first unit. And coming to the second unit, in the second unit, we try to understand how we can design various combination circuits. You can see here, I'm talking about multiplexers, decoders, encoders, code converters, arithmetic comparison circuits. So all these things are examples of combination circuits. So in the second unit, we are going to understand how we can design various types of combination circuits. Okay, so that will be the discussion in the second unit. Now coming to the third unit, we are talking about basic latch, gated SR. So all these are memory elements. So latch is a memory element. So we try to understand the basics of memory here in the third unit. So here we talk about what are the different types of flip-flops you can design, and how you can use these flip-flops to build your bigger registers. So all those things, how the flip-flop operates, how can you store data in a flip-flop. All these things we are trying to understand in the third unit here. So third unit is basically from the third unit onwards, we are talking about sequential circuit design. So first unit, basics of Boolean algebra you study in the first unit. Second unit, you try to apply this concept of Boolean algebra in order to design combination circuits. So second unit entirely talks about combination circuit design. And coming from a third, fourth, and fifth units, we talk about how to design sequential circuits. So 3 and 4, synchronous sequential circuits, and finally 5, asynchronous sequential circuits. So this is what we are going to understand in this syllabus. So at the end of the course, you'd be able to apply a simple Boolean algebra. So once you understand all these things, once you understand 5 units of material here, so once you understand these 5 units, so you'll be able to apply the Boolean concepts, Boolean algebra concepts, in order to do some, in order to bring the circuit design to a smaller set. Okay. Nowadays, people are talking about integrated circuits. So what is an integrated circuit? Integrated circuit is what? It's a bigger circuit brought down into a smaller chip. It's a big complex circuit which has been limited to a small size chip. Okay, so within the small size, there is a complex circuit there which is helping us to do so many computations, right? So how can you bring it to that size? So in order to understand these things, you require some Boolean algebra fundamentals. How can you bring down the size of the chip? Okay, so what are the things that are playing in order to reduce the size of the chip? So those things we'll understand in the first unit. Okay, how can you reduce the number of gates used in the circuits? How can you reduce the number of inputs used in the circuits? How can you reduce the number of outputs which are coming from the circuit? So all these things we'll try to understand in the first unit. How can we apply Boolean algebra concepts in order to reduce the number of logical gates, in order to reduce the number of bits, inputs to the circuit there. All these things we'll try to understand based on the concept of Boolean algebra. Then once you understand the Boolean algebra there, we apply that concept in order to design combination circuits and sequential circuits. Okay, so at the end of the course, you should be able to apply the concepts of Boolean algebra to simplify a circuit to specific number of inputs. Okay, so how can you reduce the number of gates there? How can you reduce the number of inputs? That is what we are going to, you should be able to achieve it at the end of the course. So given a Boolean expression to you, how can you minimize this Boolean expression so that the circuit can be implemented with less number of gates? The circuit can be implemented with a less number of gates. So all these things, that will be the first outcome. How can you reduce the number of inputs, or how can you reduce the number of gates for a particular circuit to be designed? Okay, so that outcome is one of the first outcome which you have to get when you complete this course. So given any Boolean function to you, you should be able to implement that Boolean function with reduced number of bits. That is the first outcome you need to achieve at the end of the course. Okay. Now talking about the second outcome, design combination circuits using fundamental logical gates and programmable logic devices for a given problem. So I give a problem statement to you. So based on this statement, you should be able to design a logic circuit for me, a simple combination circuit for me. So I want, I have some data coming. Just compare this data, and you know, output a bulb should glow whenever the output becomes one. So that kind of problem I give it to you. You should be able to design a logic circuit for that, a digital circuit for that. Okay. So those things will be the second outcome. So once you understand the fundamentals there properly, you should be able to design any combination circuit for a given specification of the problem. Once I specify a problem to you, you should be able to design a combination circuit for that. Similarly, the other outcomes will help you how you use this concept of flip-flops in order to design sequential circuit, how to create storage space. So how can you use various flip-flops to design various other types of sequential circuits. Register is one example for a sequential circuit. There are other types as well. You can have counters, okay. You can have state machines, okay. So all these things, how you design. So that forms your third and fourth outcome there. And finally, the fifth outcome will be, so nowadays everything is done using software, right? So we have, in order to design circuits as well, we have software for that. So here we use an important language which is called as VHDL. VHDL stands for Very High Speed Integrated Circuit Hardware Descriptive Language. VHDL stands for Very High Speed Integrated Circuit Hardware Description Language. VHDL. V for Very High Speed Integrated Circuit Hardware Description Language. So how can you use this language? This language is slightly different from your higher level languages. Okay. So how can you use this language to write a program for implementing these circuits? Okay. So I can write a VHDL program which can implement a adder circuit for me. I can write a VHDL program which can implement a flip-flop for me. I can write a VHDL program which can design a register for me. Okay. Which can design a register for me. So those things will constitute your fifth outcome. So you should be able to apply this VHDL programming language in order to design various combination circuits and various sequential circuits. So this is what we are going to achieve at the end of this course. Okay, so this is the essence of the entire discussion which I'm going to make in this semester. So this is a brief motivation I gave you, an introductory lecture to give you the importance of the subject there. So with that, let me go into the discussion. So now I'll stop the discussion here. But for the next class onwards, we'll discuss in detail. Okay. So online guys, are you following the discussion? Online guys, somebody please respond. I see only 40 have joined, man. I see only 40 have joined. What about others? Please inform everyone to join.